Hello, my name is Ross Sinclaire and I am the founder and CEO of Jupiter Hydro, a tidal energy company out of Calgary. And I'm coming to you 12 years after I started this thing, and I can't believe it's been that long, but here we go. I've been basically inventing and building things all my life. Something that I'm quite passionate about, and I've worked in industry. I'm a tradesman, I'm a plumber, gas fitter to start with, and I've worked on large industrial projects. I've worked in fabrication shops, I've worked in manufacturing plants, so I've seen a lot of things built. And I love building things. So when I was 30 years old, I started my own mechanical contracting company in Calgary, and that company grew to be up to 130 people eventually, and it was really the only design-build mechanical contracting company in Calgary, because everybody else was just following the drawings as you know, depicted. And so I was always questioning things and always going in the area of what's called design build. So for the last 15 years that I had my company, 90% of my work was design build. And when I speak of, say, design build, I mean that I hired the engineer and incorporated my ideas into the projects. Now this led to a place where I patented a system for high-rise buildings, and ended up putting it in 10 high-rise buildings in Calgary. So it was a really quite an expansive situation. I changed a system that was in a textbook from 1955 and redesigned it, and basically took half the water piping out of the building and saved $1 million more or less on several of these buildings, all of the buildings, some of them more I saved. I did one building called the Sate Residence in Calgary, where we heated the entire building through the walls and incorporated my patented system as well. You can see more about that on the Jupiter website. You can see some of the patents and some of the things I've done in that way. At any rate, in 2010, I was watching TV, and I saw a program on the failure of the, no, maybe it was 2009, a failure of the tidal turbine in the Bay of Fundy, open hydro turbine, and I got very interested in tidal energy and started researching it and looking into it, and I thought, my goodness, there's got to be a less complicated way to do this. And so I don't know where these ideas come from, but I basically got the idea of using an Archimedes screw, an auger. And these augers have been around for 2,500 years, so I won't take any credit around that. However, I thought that if that's the most efficient way to move energy, move a material, whether it's water or grain or sewage or whatever it is, from one place to the other, it occurred to me that the opposite was true. That when you present a flow of water to this Archimedes screw, if you do it right, it's going to transfer into rotational torque in a very efficient way. And that has actually proved to be true, because when we tested our last prototype in the Hydrokinetic Turbine Test Center in Manitoba, they told us it was the most efficient turbine they'd ever seen or ever tested. And it's actually 25 to 50% more efficient than really any of the others they've tested. So I went about doing this, and I ended up saying, going to my patent lawyer and saying, can I patent this? And it turns out I could. And the patent is a very strong patent because it relates to the angle of the water hitting the screw. And that angle is, the optimal angle is about 30 degrees. So I've patented a range around 30 degrees. And then there's an optimal pitch, which means the distance between the turns of the screw. And the optimal pitch is 60% of the diameter. So my patent covers from 30 to about 120% of the diameter. So it's a very, very strong patent. And this patent is now completely in place in 23 countries with one more pending. So, if you want to see all the different steps of the prototypes that I've done, take a look at Jupiter Hydro's website. There's a real progression we did. We did testing in the University of Calgary. We did testing in the Fraser River in Vancouver. We did testing in the Hydrokinetic Turbine Test Center in Manitoba. And this basically led to me coming to Nova Scotia and promoting my ideas, and at first it wasn't very well accepted that I wanted to put a floating turbine in the water. They said, well, that's not the way it's done, but that's actually changed pretty dramatically as well. So in 2019, after many years of fighting away and hoping I could get financing to do bigger and better things, I got a power purchase agreement for 2 megawatts adjacent to the foresight in the Bay of Fundy. So that power purchase agreement is worth about $30 million over the next 14 years. So that's very exciting, and I wanted to kind of take you through the process of what I've learned, because there's been nothing but failures in the tidal energy industry. There's nothing really proven at all right up to this date in 2022. And I always pondered as to why that might be. And so I'd like to share my thoughts on that. I may be a little off, but I'd like to share that. So I'm just going to grab this other item. If you take a typical windmill, 3-bladed windmill, that is obviously a very, very proven technology. This is just one mounted on the ground somewhere, and they're made by all the major manufacturers, and the predominant system that's used throughout the world. And so that's taken 20, 30 years to really fine-tune it and prove it, but they're making them bigger all the time. So that's fantastic, and it's great for the planet. Now, I think what happened when people started taking after the idea of the tidal industry, they went into the idea that, well, we can put this in the water. You know, let's say this is a floating platform, and they put it in the water. And I think there's a few issues with that. And in engineering, they call it fatal flaws. So, you know, you can suit yourself on that one. But when it's up in the wind, it always straightens out to a 90-degree where the wind's hitting it. When you put it in the water, there's a lot of other forces involved here. So you can have waves coming from a certain angle or whatever, and now you're off balance with this thing. And an off-balance set of bearings is a big, big, big problem. The other thing about the water is it's 800 times more dense, so it's not forgiving in any way, shape, or form. And it has different flow rates as you go up the water table. So the bigger you make this, the more struggle you've got, because the speed of the water here is going to be different than the speed of the water here. That throws things out of balance too. So you've got a situation where there's all kinds of forces that are struggling. This is really not flowing with natural forces at all. It's fighting against them, and I think that's a big problem. So we're going to look at the biggest tidal turbine in the world to date, or an example of that, and that's here on the floor. It's a unit built by, I think you can't help but recognize it, by Orbital, and Orbital has built the most successful and largest floating tidal turbine in the world, and proved it in Orkney for, well, I don't know how many months, or not much more than a year, if it's been a year or whatever. And I want to kind of go through what I see happening in those tidal flows. Now there's 4 anchor chains on this particular unit, and so if the water is coming in here, the tide's coming in here, and you're down low tide, and it's coming in, it tightens up on these chains, and these things are turning like crazy. It's generating, everything's great, and then it gradually builds up and up and up and up, and then it stops. And when it stops, it stays still for maybe 10-15 minutes, and then it starts going the other way. So when it goes the other way, it tightens up on the back anchor chains, and everything's fine. It goes up and down with the tides, and I feel like if you don't have any other forces involved, this works great. But what happens if you've got a side wind, or even an angle wind that's coming from here or here, and this unit stops and doesn't get tightened up on the anchors for an hour and a half, whatever, and this starts going crooked, because you have no way of steering it, so it starts going crooked. So now, when it tightens up, it's fighting to straighten up again. It's 260 feet long, so, and it's the water line's halfway up on it, so it's got a real battle on its hands. It'll take a long time to straighten up, and the whole time that's happening, these are out of balance. And you know, I think that's a major problem with this situation. Now the other problem is, at one point they designed this unit to weathervane, and now it just goes, stays in one place. So when the tide's going this way, it's running into the generator, the swing arm, and that's creating all kinds of turbulence. So that's another unbalanced situation for the unit, and certainly it's not going to be anywhere near as efficient with the water moving this way as it is with this way. So in my mind, that's what you might call a fatal flaw as well. The other major issue that's happened with floating turbines is the power cable. Now, 80% of them have failed in no time at all, because there's very harsh, most of them been tested in Orkney in Scotland, and that's a very strong tidal flow, and there's tremendous amount of force on this power cable. So this power cable, they put bend restrictors on it, but the bend restrictors can only go so far, and then they play with the idea that they have what are called a flying S, and you know, I guess that works to some degree. I find it kind of questionable as well. But the bottom line is, this thing's going like this. And that means the power cable's dragging on the ocean floor, and that's a big problem over time, because the ocean floor is full of rocks, and sharp edges and valleys and whatever. And so I've always seen the power cable as by far the biggest challenge to a floating turbine technology, which I have. So I've been very concerned about how do we deal with that. And I really haven't had an answer for that for most of my last 12 years. I've had no answer for it, and so in many ways I've been pursuing river power instead of the tidal, because I thought, you know, what if we go in there and we raise some money and we fail? We'll just be like so many others. And so I've had a couple really powerful things happen in the last few weeks that, or last few months, that have changed my attitude. That the two major things has been the power cable, and the second thing has been, can you make a screw that'll last and stand up in really harsh tidal flows. And I've been recently introduced to the founder of Composites Atlantic, who is as accomplished as any composite person in the world. There's airplanes flying all over the world with his technologies in it. He's just an incredible engineer and manufacturer of unique composites. And so I feel like his name is Maurice Guiton, and Maurice has assured me that he can build a screw turbine that will last for 20 years in the water. So that's taking care of one of my major concerns. The second major concern, of course, has been the anchor cable. And what we've done now is we've come up with a solution for that, which is I'm really excited about. And this came in discussion with my good friend and engineer Greg Farrell, who's the owner of GRF Structures. And Greg said to me, why don't we make the swing arm solid? And so this is a solid oval swing arm with a hollow, solid steel, with a hollow through the middle, so the power cord goes down through there. So it's totally protected. And that's what we've come up with for my second major concern about this tidal process. So we've got, I'm going to put my back to the camera here, but when you've got the tide going out, let's see, it's up high, so it's going out of the minus channel, the Bay of Fundy, and it comes along and it tightens up on the anchor, pardon me, the anchor rod here, and it goes and eventually runs and runs until it stops. It goes down 30 feet, it stops, and interestingly enough, the angle of the water coming in is about 12 degrees different than the angle of the water going out. So everything being equal, this thing's just going to turn around, the water's going to start running the other direction, and this is just going to turn around. So it turns around, whoops, and it tightens up, and the water comes in and goes up 30 feet, and you generate. Now, when that's finished, because of that other angle going out the same way, it's going to turn around this way to go back out. So this has solved any issues around the power cable. Now you might say, well, what if the wind's hitting it and it goes the other way? Well, I don't want to go into the physics of that right now today, because we have an answer for that, a really simple one as well. And so I'm really excited to now say that we are very confident that we can build a this 2 megawatt turbine. These are 500 kilowatts each, and they're 2 turn one way and 2 turn the other way, and they're 25 feet in diameter and about 75, or oh no, only about 60 feet long actually. And that's pretty big. So each one will produce 500 kilowatts. So this is a 2 megawatt tidal turbine, which is the same rated capacity as the orbital one, but I feel like it has a whole bunch of inherent advantages. So we've pointed some of those out. I would now like to go to the water in Dartmouth. I'm coming to you from my garage here in Halifax, and we've got a really good stream in Dartmouth that we've shown some of this stuff in, so we're going to go to some videos there and see how that functions in the water and talk about it after after we come back from looking at those. Okay. This is our little turbine in a stream in Dartmouth. As you can see, there's 2 screws one direction and 2 the other. This is moving along at about a ½ meter per second. The speed in the Bay of Fundy is 10 times that, at 5 meters per second. Just thought I'd show you how our noodle model works. Okay. To begin with, we've started with a very slow flow rate here. It's only maybe about 1 foot per second, and I'm showing by turning this that it speeds up as you get it to the optimal angle, which is 30 degrees to the flow. We're now tipping it down so that it shows it tip down at a 30 degrees to the flow and get very similar results. The third way we do this is by putting it halfway in between, being partially tipped down and partially tipped out. As you can see, we've moved to a location with much faster moving water, and also the screw is turning like crazy here. With flow rates similar to this and an 8-foot diameter screw, we would make 50 to 60 kilowatts. And if we upped it to 24 feet in diameter, we would get up to 500 kilowatts. 4 of them would total 2 megawatts. Okay, we're back in my garage here, and there's a few more, hopefully those videos show how well this functions in a little flow, very slow flows. I want to touch on a few other points, and one major point is when you've got a generator that's 500 kilowatts like we have on these units here. There's a danger of the screw turning too fast, so we're making 500 kilowatts at about 3.5 meters per second flow. The flows on the flood going into the minus channel there are up to 5 meters a second. So when you've got a bladed technology, you have to tip the blade similar to what they do with the wind turbines. However, again, that creates a whole bunch of complications with the bearings and moving parts down in the water. I will mention that I think General Electric found that out very clearly. They spent about $200 million, and they had 40 engineers working on a 3-bladed turbine that went in the ocean, and in 2017 they said they walked away from it all and reassigned the engineer somewhere else, and they basically made an announcement that they felt it was too expensive and they were never going to get the cost down. And I think that probably was a very wise decision, because it is too expensive and too complicated, trying to do a bladed turbine. So our answer to the overspeed is with this screw, we simply tip it up to a less optimal position so that when we're at 3.5 meters per second and it goes up to 4 meters a second, you just tip it up a little more and it still produces 500 kilowatts. When you get to 4.5 meters per second, you tip it up a little more and it still produces 500 kilowatts and the same. So it's very, very much the same. Our idea that's behind everything is very simple answer to complicated situation there. So the idea of this screw bearing, if you want to compare our bearings with the bearings on the bladed turbines, we have a composite bearing holding this thing in place. And I can turn it this way. It's holding it in place at a 30-degree angle. So all the forces are on this way and on the bearing that way, which it's designed for. The bearings we use are used in props for big ships and stuff like that. So they're very much designed for this kind of forces. We think they'll last for 20 years. So if you've got that happening and you've got some side issues where the wind's pushing you and you're a little off square and you're not tightened right up to the full extent because you've got side winds and all that, it really doesn't matter because it's all the same forces. This is going like this, who cares? It's all the same forces. So we're not affecting anything, whereas being off the angle of square to the water flow is a major issue with the bladed turbines. So I wanted to make that point, and now I want to talk about costs. The costs for this unit that we have here is, I've done an awful lot of budgeting on this and connected with all the people that are going to do all the different processes. And for example, the generators are off the shelf. We buy them from a Bulgarian supplier. The bearings are off the shelf. They're very proven. The screws are going to be built by Composites Atlantic, and we're very comfortable with that. The barge is going to be built by GRF Structures, who is the guy that contributed to this fantastic idea. He's an incredibly outside-the-box thinker, and he's got a shop that's 180 feet long, so it's perfect to build our whole turbine unit. And he will build the swing arms as well. The power conditioning that goes in here for the inverters and rectifiers and transformers is all standard equipment, and that will sit on the barge here. So the power goes on down the line, and we plug into a line that goes to shore. Now that line doesn't get beat up because it's laying on the ocean floor and it's armored. And so we're going to build this whole thing in, set that down, we're going to build this whole thing in Dartmouth, right close to the dock. We're going to assemble it in the dock. We're going to put the big long swing arm on it, which is about 250 feet long. We're going to pick it up. And it won't have that weight on there, but we're going to pull it by the swing arm down around the south end of the Bay of Fundy and on up and into the minus channel, and we're going to set it down on the pre-drilled anchor and plug it in. Now you can't get any simpler than that. So this is what we've come to, and we're very excited about that because it is so simple. And I've always felt that you've got to simplify things. Always simplify things. Basically, we've done about 30 different designs for these screws and for rivers and sitting on embankments and doubly deep and V-shaped where you're in shallow water, so you have them at a 30-degree angle in the V-shape. That's called the delta unit. So we've looked at so many different ones, and we finally came to this one for the Bay of Fundy. And entitled in general, this is the most efficient layout for all of us. Now I think that kind of thinking hasn't really taken place when you're trying to take a bladed turbine and you just keep trying to do the same old. You're starting off with the wrong premise. So this one's very much in harmony with the flow of the water. It doesn't affect the fish at all because they roll right through. The debris, the trees and all that kind of thing, the branches, they roll right on through the screw turbine. We're the only technology with the generators out of the water. You know, I don't see that it's such a good idea to have generators in the water. So when you go to repair these generators, we can have a spare one sitting on the barge and have just a little $2,000 lift with two guys to change out the generator. This maintenance is just hugely simple with this system. So we'll look at overall costs. This turbine that I've pointed out from Orbital, it's been announced they spent 26 million euros to build it and deploy it in the Orkney test site, and that's about $35 million. I am very confident we can build and deploy this in the Bay of Fundy for less than $10 million. That means we're less than 1/3 the cost to build and deploy. Now let's look at the anchoring here. There's 4 anchors on a typical floating barge. The different technologies, they all use the idea of 4 anchors. We have 1 anchor and no problem with the power cable. So I would suggest to you that our anchoring system is 1/3 the cost. Now I also believe, because of the simplicity of this and the ease of maintenance, that our maintenance is 1/3 the cost as well. Now that lends to a situation where you're, what's it called? I keep forgetting that. Levelized cost of energy. I never remember that. Is 1/3, our levelized cost of energy is 1/3 the cost of all our competitors. Now that's a bold statement, but I can back it up, and that's part of what this video is doing. So the EU has targeted, I think for 2027 or 2030, they've targeted, they want to get the price of tidal energy down to, I don't know, 100 euros a megawatt hour. We're way below that right now. So I feel like there's a huge opportunity for us to go into sites in the UK, Wales, Scotland, France, Ireland, that are, some of them are licensed already, other ones are, they started licenses and they walked away, but there's literally hundreds and hundreds and hundreds, probably 1 to 2 gigawatts of sites that are partially licensed or licensed that this technology can go into. So we could spend the next 30 years in the UK and do nothing but tidal energy systems there, because that's what's available, and I don't think the competition will be able to hang with us at all. Now, because I'm a builder, I don't have any intention to send this out to you know, a team of engineers and then bid it out to a bunch of different manufacturing plants and all that kind of thing. we're going to build it. We're going to build it ourselves. And Greg Farrow from GRF Structures has already told me he would love to join forces with Jupiter Hydro, and we'll build a plant up in Scotland. The government will give us half the money we need for the new plant. We'll hire all local people and we'll start building these things. And we'll do it very efficiently and very effectively with all the newest technologies and automatic welders and all these kinds of things. I'm very, very familiar with all the best practices to build something like this efficiently. And we'll do nothing but take the costs down. So I think I've covered just about everything, and certainly you can connect with me and I can answer any questions that you may have. We are excited to be going forward with this, and we are very passionate about creating green energy for our planet. It's very important to me. Thank you.